Hey, how's it going, YouTube? We've got another day learning pure mathematics out of this beautiful book by Serge Lang. Welcome back. Today is August 11th, and today's technically episode 9. We've got Luna. She's going crazy right now, so hopefully she'll make an appearance coming up soon. So thank you for tuning in. I'm excited. I can't believe how much success those videos have been getting, and just the fact that especially the series intro just keeps performing. I just cannot believe it, man. It's about to cross 250,000 views. That's insane. That's so many views to me. I can't believe it. Thank you everybody so much. All right, so I wanted to try a slightly different format in today's stream. We should have my background music going. These are my recordings as a guitarist. And then somebody in stream today commented hey, consider trying to make the iPad larger. So we're gonna try to have a wider iPad in landscape mode. So today is episode 9, as I mentioned. What are we doing today? We are going to be doing a review episode. So we're just going to be working exercises and reviewing each of the topics that we've done so far. So we're going to hit an exercise from section 1.2, 1.3, interlude point 2, and then 16.1. So I'm excited. First, I always like to try to respond to a comment here. So thank you, Malcolm, for this nice comment. I'm a math teacher and agree completely with what you've been saying. The big barrier is that we have existing standards and curricula that say what skills students must have at the end of our courses. And there is so little time to teach it all that we can rarely squeeze anything else in. Trying to break from it when I can, because I do believe that teaching kids mathematical argument and reasoning is so much more valuable than much of what we teach now. Yeah, man, I mean, this is something that I think about a lot. My thesis here is that some of the most beautiful parts of math are the things that our classrooms, at least in the US, I can only talk about the US, that we're skipping. We're just neglecting to share more advanced, or it's not that it's more advanced, but more pure mathematics. Yeah, pure math, proof-based math, more conceptual math. And that might not be motivating for everybody. That really would be demotivating, I think, for some people. For some people who hate math, there are a lot of people out there who really hate math, to tell them hey, let's learn some extra stuff that's not even going to be on the test, and this isn't even going to help you at all get into college, but trust me, bro, you're gonna love it. This is gonna make you want to learn the other stuff. This is just extra work I'm giving you. That does seem irrational. I think that kids who are checked out and not really interested in math are not going to get motivated by having to learn extra math. So it's a major kind of challenge and issue. My thought is that if I were a teacher leading a classroom, I would want to try to share some examples as the exercises. So to choose interesting exercises, basically. Your homework is always interesting homework. There's a reason that you're doing this problem. I'm telling you, by the way, this is used in a later subject or something. The first problem that we're about to do from Lang, he even says in the second problem, he says, by the way, these are called polynomials, and you can read more about these later in chapter 13 if you're curious. That's a simple example, but I can think of other examples of definitions of functions and other things, and relating that, connecting that to something in the real world, to my experience working as a software engineer. my thought is like, if you can choose interesting exercises so that the homework is motivated by pure math facts, like that can be, I think, motivating, and it doesn't add extra work necessarily. Like, rather than doing a bunch of homework exercises that aren't connected to anything, it's just drilling, just kind of rote memorization or just pattern memorization. But doing something like proof by induction, that's going to be hard, I think, to try to get everybody interested in, because it's not tested on the SAT. And I guess I just think that it should be. I wish that it were covered on standards, and I wish that we could remove some topics from the standard curriculum. But yeah, anyway, so thank you. I completely agree. If anybody has any thoughts about this, please leave a comment, because I think that this is a really interesting point. Standards-based teaching is important as a teacher, but then you don't want to have to just teach to the test, right? Like, it's partly why I'm a little more interested at the moment in teaching at a private school, like somewhere that doesn't teach 100%, like the funding for the school isn't directly tied to like performance metrics on standardized test exams. So I don't know. Yeah, it seems like a hard thing. Right now, I don't think I've updated you all. I did not get that role that I was shooting for, and it's okay. I think that the other candidate was much more qualified, and they liked me a lot, and I'm going to start subbing, so that's really exciting for me. I'm looking forward to it. Just starting to sub, and it means that I'll be continuing to go hard on trying to build this channel and this YouTube. So thanks everybody for being here for this journey. All right, rules for addition. First one, justify each step using commutativity and associativity in proving this identity. So I want to just work this by hand in real time. I think that there's something nice about seeing somebody actually working a problem like this and talking through it rather than just tapping and revealing a solution, right? So we start with the left-hand side, and we want to rewrite the left-hand side until it becomes the right-hand side. So let me move this right over here to have enough space. So ultimately, I want B and D on the left and A and C on the right. This is an interesting way to combine these, but let's work these. So if I want B all the way on the left, I can rewrite subtraction of B as addition of negative B and subtraction of D as addition of negative D. In fact, I will do that throughout and drop parentheses as well. So the left-hand side is the same as this. And it said justify every step. So justifications for this are definition of subtraction and associativity. So by definition of subtraction, A minus B is the same as A plus negative B. And associativity says that we can remove or regroup parentheses. And now by commutativity, this is negative B plus negative D plus A plus C by commutativity. Now, I forget the number, the property number for this one, but in Lang, we know that we can factor out the negative. So we haven't yet defined multiplication in Lang, so it's not that we're factoring out -1, but that the inverse of, well, yeah, let me finish writing this first. So I know that I can factor out that negative sign by property N5. N5 says that we can do this. Then, well, what we can do, we want to get to minus negative a minus c. Well, I think we would write it like this. Negative c. So I'm using right now the property N4. N4 says that you can rewrite a as negative a in Lang. So that one was by N4. We need another page. Y'all, please do let me know what you're thinking about. I don't know, how is the series going? Like, what are your thoughts? Do you like this format? Do you like more problem solving together style like this? Or I don't know, just generally, what would you like to see out of this show is, I guess, what I really want to know. So now this, again, we can factor out that negative sign by N5. And, well, I use definition of subtraction as well in this. Here, let me slightly fix that. So plus negative c. So this is by N5 again. And then on the last line, we can again say that adding a negative is the same as subtraction. So this is definition of subtraction. Cool. So now we're done. That's this exercise. That's it. Awesome. Next, rules for multiplication. Expand as a sum of powers of x multiplied by integers. These are called polynomials. All right, so solution on this, we use the square of a difference identity. To remind ourselves what that looks like, the square of a difference is a squared minus 2ab plus b squared. So this is one of those quote-unquote poems that Lang had in that section. So now, where a is 1 and b is 2x, then 1 minus 2x quantity squared is 1 squared minus 2 times a times b plus b squared. Let me add another page here. Cool. Let me move a bit of that might be clipping out of the screen. All right, then we've got this. Okay, I thought Luna would be showing up a bit more today, but 1 squared is 1. Here, multiplying 2, 1, and 2, we get minus 4x. And then 2x times 2x is 4x squared. If I wanted, I could... I mean, this is a perfectly fine way to write it, and in fact, it matches the format of the... Lang writes the constants on the left and then the x terms later. It's a little more standard to rewrite this with as descending powers of x. So this is a polynomial, meaning it is a sum of powers of x. This one is a quadratic, meaning that it's a degree 2, but you don't need to know that right now. Like, we don't need to know that there's something called a quadratic formula. We don't need to know any of that sort of stuff right now. All this is a square of a difference and using this property. What the x is doing here is that we can... Like, this is going to be a pattern no matter what x is. Like, 1 minus 2 times 3 squared is ... stuff, right? Or 1 minus 2 times, 12 or something. Like, x can be anything, but these are two evaluations where x is a specific value. If I computed this form, we'd have 1 minus 6 squared, which is negative 5 times negative 5, which is 25. Or on this one, we'd have 1 minus 24 quantity squared, which is negative 23 quantity squared, which is, I don't know what that is, a larger number. Doesn't exactly matter what it is. 200, what would that be? Um, 289. Is that correct? Did I get that correct? I feel like I did not get that correct. Okay, well, the ones place is correct. 23 times 23, ooh, 529. What happened? Oh, shoot. Oh, I had a subtraction here that should have been a positive. Okay. 529. Yeah, there it is, 529. I was thinking of that the subtraction was canceling out. Yeah, I see what happened. Okay, anyways. I just evaluated specific values of x for this polynomial. But now we could see, does this evaluation also work? So if I use that approach, 4 times, in this case, I used x being 3. So what is 4 times 3 squared? Minus 4 times 3 plus 1. Oops. Plus 1. That's 4 times 9. Minus 12 plus 1. 4 times 9... Let me move these things. 4 times 9 is 36. Minus 12 plus 1. So that would be 24 plus 1, which is 25. And so we see that we get the same value either way. and we proved that this format of this polynomial, this factored form of this polynomial, is the same value as this expanded version of that polynomial. Where x we can allow to be a variable. I evaluated the value of that polynomial when x is 3 and found that it was 25. Okay, so there's that. Now, De Morgan's laws. Let's see. Let's work this one. I'm only going to work the first one. To prove that these two are equivalent, the if and only if symbol is this double arrow. We want to show that a truth table for both of them have the same values. So I got some feedback after the previous video that was super correct, super true, that I shouldn't have used blank spaces. I was getting too clever, I think, with some of that stuff. I should use zeros, so I apologize for that. For those who watched episode 7, I think it was, I think I really should just use zeros. So here we go. I'm putting in all of the possible values. A can be true, B could be true or false, C could be true or false. Hello, Luna. And what else do we have? 0, 1, 1, 0, 1, 0, 0, 0, 1, or 0, 0, 0. Yeah. So now this, I think, captures every option. The first of these two terms, A and B or C, A and B or C, I'll write it there, and this is our goal, but I need some scratch work in order to understand that one. And same on the right hand side, A and B or A and C. I don't quite have enough space here, so I'm actually going to do my scratch work in place. So it's like I'll write in it and then erase. So A and B or C. In this case, A is 1. 1 and B or C, 1 or 1. 1 or 1 is 1. 1 or 1, 1 and 1 is 1. So true and true is true. In the second case, we have 1 and B or C is true. Because B is true, it's okay if C is false. B is true, so B or C is true. That one is still 1. You get better at these as you do them a bunch. So A and B or C will be 1 and 1. And now this one is 1 and 0. True and false is false. Now, all of these will be false. Why is that? It's because we need A to be true in the and. And all of these are 0 and something. 0 and either true or false. False and anything else is false. Next. So now we've filled out the full truth table for the first of De Morgan's laws. Now, A and B is true. A and C is true. So 1 or 1 is 1. A and B is 1. So if the left side is 1, I don't even need to evaluate the second part. A and B was true, so the second line is true. A and B is false, but A and C is true. Now the next one, A and B is false. A and C is also false, because A and C is 1 and 0. 0 or 0 is 0. So that one is false. And all of the rest have the same argument that they require A and something else. So all of these are of the form 0 and something, or 0 and something. Well, 0 and anything is 0. And also, same thing here, 0 and anything is 0. So then this is all 0 for each of these. So now, the truth table has the same exact values in every possibility of A, B, and C. So therefore, De Morgan's law, first law, is true. This is just like in coding. You all have people who have commented in the comment section that this reminds them of coding. It's because it is just like coding. In coding, we would write these Boolean things as A and B or C. You can refactor this as A and B or A and C. This is just the coding version of De Morgan's first law of the two. Kind of ugly symbols. I don't like the ampersand. Some coding languages will just use the word and, which is nice. A and B or C. But in any case, there you go. There's a little bit about logic and filling out a truth table. Hope you enjoyed that. Now, induction. This one is fun. So, prove that this identity holds. So, proof. First, we don't need to do this. This isn't part of the proof. But it's good to get some evidence, I think. Some evidence. Like, practice this problem for yourself. What is 1 squared plus 2 squared plus 3 squared? That is 1 plus 4 plus 9, which is 14. What is 3 times 4 times... So the right-hand side, when we substitute 3 into the right-hand side, we have 3 times 4 times 6 plus 1, which is 7, divided by 6. 3 times 4 times 7, 12 times 7. 12 times 7 is 84. Divided by 6 is 14. Yep. If you don't see that immediately, maybe we reduce this once. So the numerator and denominator are both even. So we can factor out a 2. 2 times 42 divided by 2 times 3. Right? So I can cancel a 2. Wait. Oh, yeah. 42 divided by 3. And at this point, you just need to know that you can divide 42 divided by 3 is 14. You can go to the division algorithm like this. 3 divides 4 one time, and then 3 divides 12 4 times with no remainder. So there you go. But the way I see it is that 42 is 30 plus 12. So I knew that 30 is an easy multiple of 3 to work with. 30 is 3 times 10, and then 12 is 3 times 4. So therefore, 42 is going to be 3 times 10 plus 4, which is 42 is 3 times 14. All right. So there's one piece of evidence. I tried substituting in. I checked that this identity holds for the number 3. All right. Now let's do the real proof by induction. First, the base case is true. As the left-hand side the base case is true as 1 squared is equal to 1 times 2 times 3 divided by 6. Where did I get those numbers? We can see it is true that the left-hand side of this is 1. 1 squared is 1. And the right-hand side is 6 divided by 6. So it is true. But this part is the left-hand side with when n is 1, and the right-hand side is here when n is 1. Because on the left of this identity, you only have one number in that list, and then in the right, you substitute n being 1, so you get 1 times 2 times 3 divided by 6. Okay, so the base case is true. Next, assume the identity is true for some n greater than or equal to 1. So we know that it works for n equals 1, and therefore it must work somewhere, at least at 1. And let's just assume it works up to some point. We show that the identity, the equation. Somebody asked what an identity was. I mean this equation is true. This is an identity. Oh, how far back was the iPad frozen? What's going on? Why is the iPad frozen right now? It doesn't look like it's too long ago, thankfully. Okay, we're back. Thankfully it wasn't too long. Alright, so we gotta wrap this up. We showed that the identity holds for, also holds for n plus 1. So, what is the left-hand side for n? When n is n plus 1, it would be this. Now, we can group the first n terms like this by associativity, And by the inductive hypothesis, we're assuming that that first portion is equal to the claimed right-hand side, because we assume that this identity is true, and then we want to show that the equivalent equation is true when n is n plus 1. So we assumed that the equation is true for 1 squared up to n squared, and now we want to see what happens when we add n plus 1 squared. Well, we could do this. So this requires just some amount of knowing how to work with fractions, which we haven't technically done yet, and I want to acknowledge that. So if you feel like you need a review of how to add fractions, feel free to peek at the book, at the section on the rational numbers, which is another way to say fractions and adding fractions together. What I did here is converting the second term to a least common denominator. We can multiply any number x. We can write any number x as 1 times x. And then I can rewrite 1 as a divided by a for any number a not 0. As long as a is non-zero, I can always rewrite 1 as a number divided by itself. For example, in our problem, we did this path. X is 1 times x is 6x divided by 6. Yeah, and then we are using the fact that a divided by b plus, well, let's do a divided by c plus b divided by c is a plus b divided by c. I think that we need to show this and understand the theory a bit more of why this works, but right now for this proof, I'm assuming that we believe this and that we have seen this before, how to add fractions, even if we haven't treated it carefully yet, which is a perfectly okay way to work through a book like this. Okay, now, something that's cool is that at this point, if we think about it, we do have a common term, because n plus 1 squared is n plus 1 times itself. So maybe I just briefly rewrite this just for clarity. Now, I can factor out n plus 1 on the left. So I keep saying the term factoring, and somebody told me that we haven't done a lot of theory of factoring yet, but factoring is just another way of saying distributing. It's just using the distributive property that we've been using all the time. Like in the section that we're working, we've been using this distributive property. It's just that oftentimes we have a mathematical equation or something of this form with a common factor on the left. Now, by the distributive property, we know that this is the same as this. It's just that we're going in the other direction in some sense. But it's still the distributive property. It's still the same math fact. It's kind of like if we go this direction, we call it factoring. Whereas if we go this direction, it's like we call it distributing. So right now, the common factor that I see is that both of these are multiplied by n plus 1 here. So I'm going to factor that out, or reverse distribute that here. We got to wrap this up. Oh my gosh, it's already later than I wanted. If I distribute this n, though, into this term, we have 2n squared plus n, and then we have 6n plus 6 from this portion. So I did 6 times n and 6 times 1, and I factored out that blue n plus 1 term. All divided by 6. Now, n plus 1, here we have 2n squared plus 7n plus 6, all divided by 6. At this point, we may get stuck or stumped or something, but thinking of the problem-solving skills, what we want to get to is the right-hand side with where n is n plus 1. The regular right-hand side is like this. So the right-hand side with n being n plus 1 instead would have n plus 1, n plus 2, 2 times n plus 1 distributes as 2n plus 3, all divided by 6. So we got this left-hand side to a pretty good place here. What we can do now is say that the right-hand side for n being n plus 1 is this thing, and I can distribute here. N times 2n is 2n squared. N times 3 is 3n. 2 times 2n is 4n. And 2 times 3 is 6. All over 6. And now 2n squared plus 7n plus 6, all divided by 6. So I would say, that this equals, we could call this the middle, right? And we could call this part the middle. Therefore, the left-hand side equals middle, right-hand side also equals the middle, so the left-hand side also equals the right-hand side. And then therefore, now we are complete. Now we are done. We've completed the inductive step this way. And factoring, doing this factoring direction, I wanted to really talk about this based on the feedback recently. Factoring is something that we do a lot of practice with, and I've seen a lot of kids get stuck and really stumped with factoring. And I wish that we would teach it as reverse distribution, or we don't we don't really emphasize the distributive property, I think, enough. And we haven't seen these specific examples. Like, here's a place where we see factoring being useful. And to factor something like this, we learn some patterns, typically. And there's something called, like, there's something called, like, the rational root theorem and some other things that you can use here. But you kind of guess, like, if it does split to linear factors, we would want an times cn, an times cn needs to equal 2n squared. So ac is 2, ad plus bc. Yeah, this is fairly tricky to get good at factoring something like this. We will do it in a future video and get a lot of examples of these. But what I'm really trying to get at is that if you know your goal, if you know what it is that you are wanting to factor to, it's much easier because we can just distribute. We can just see what happens if we distribute these two terms. And then, we end up seeing the same middle point, like going from the left and going from the right. All right. Well, thank you, everybody. That ended up a little bit longer than I was hoping for. Luna has been Luna today. Hi, Luna. I hope you enjoyed it. Thank you, everybody, for watching. This was just a little longer than I was hoping for. Super special thanks to everybody who is helping support the channel one way or another. There's all the people who are hanging out with me in the live streams and helping me learn advanced mathematics. There's all of the hobbyists, including these new hobbyist members. Thank you, Fred, Bidiendu, Dave, James. Thank you so much, everybody, for all of your support, and all of the new Luna members. Oh my gosh, dude. Like Lord Nova, Frederica, Christina, Pete Gouge. Dude, thank you, everybody. J Russell 26, dude, thank you. Crossover fan from the other channel. I really, really appreciate it. Your support means so much, everybody. So thank you for being here. Take care. Bye. Bye.